Good morning, folks. So, how's Lab 3 going? Anybody work on it over the weekend? What happened? Did you get a node working?
Well, we tried to copy the MATLAB code without any memory blocks or anything.
So you can certainly do one node.
Yeah.
So you take one node and you tie it to 4 stationary nodes, so these are all fixed at 0. And this thing, then, if we look at it from the side, the mass is going to go up and down, and it's simple harmonic motion. So you can do all the arithmetic. You can average together the spring difference lengths and multiply by rho and do all that kind of stuff, and do it with just one node, which is probably a reasonable way to start. And once you get one node, then you can duplicate it. Yeah, so you would start out with duplicate nodes, and then at some point it's going to get awfully unwieldy when you had to start trying to make thousands of nodes. You will run out of registers or memory or multipliers or something. So then you have to start figuring out how you're going to actually parallelize it. So Friday I gave a couple of possibilities. One is to say, I'm going to take 4 nodes and I'm going to compute them in serial, 1, 2, 3, 4. But the order of the state machine is going to be read all of the inputs. So read all inputs. Calculate 1, 2, 3, 4. And since we're doing them in series with a state machine, one after the other, we only need one multiplier for the 4 nodes. And then you write all outputs. And that ends the step. And every set of 4 nodes would be synchronized with the same state machine. So everybody reads at the same time and writes at the same time. And that scales up pretty well. With 4 nodes, you have 1, 2, 3, 4, 5, 6, 7, 8 I/O wires. With 16 nodes, you have 16 I/O wires. And you could go somewhat higher, probably in the region of 64 nodes, without running out of time to compute in the state machine, because you have about 1,000 cycles between audio samples. And that's an easy way of scaling up the computation. At some point, you can no longer keep individual values in individual registers within the structure of the FPGA, because you will run out of registers. You need about 36 bits or so per node. So, did any of you look at, let's see, an MLab block? An MLab block is 32 bits by 20 registers. So that would give you enough for 10 nodes. You could also use a M10K block, which I believe is about enough for 256 nodes. It's about 256 nodes worth of memory. So that would be a 16 by 16 block. Yes?
The MLAB blocks are just concatenations of logic blocks, right?
MLAB blocks are concatenations of logic blocks, and the documentation is a little hazy, but I think what they're doing is they're treating the 6 input lookup tables as RAM. And so they're allowing the logic to modify the lookup table.
Okay, so it's more efficient than just using the registers in the logic unit.
Correct.
Okay.
By a factor of 4 or 5, something like that. Yeah. So those are various possibilities given that you want to break down the system into square or more or less square chunks. So how many I/O lines on a 16 by 16? Let's see, it's 4 times 16, right? So only 64 outputs for 256 nodes. So it scales well. As the area goes up, the number of I/Os per calculation goes down. That's always a good thing for parallel computing. It's all nearest neighbor communication. That's nice, very regular. So one student posted a copy of the equations I talked about last week on Piazza. And does that mean that people want to see those equations again? The recursion equation that updates the drum? Or that was kind of a public service on Piazza? Or what? I did modify Lab 3 slightly to add a reference to the nonlinearity, physically based synthesis of nonlinear circular membranes, equation 10. Is the model I used for the nonlinearity I gave you last week. Are there any questions on this at this point? Oh yes, the spectrum. Slightly obscure, but the spectrum of a square drum you can solve, analytically solve, and the modes go as the square root of m plus n, where m and n are small integers. So the lowest frequency, the fundamental of the drum, is square root 2 in some weird units. If you were going to fit the spectrum to a drum, you would play your drum into MATLAB, take the Fourier transform of it, and scale every other frequency to the square root of 2. So this is the fundamental, and then this frequency is the square root of 2 over the square root of 5 over the square root of 2 times the fundamental, and so on. So don't try to calculate the fundamental for first principles. You can measure that, and then every other line of the spectrum should more or less fit. Depending on how many nodes you have, there starts to be some fairly serious inaccuracy up here around the 7th or 8th mode. And I would say that you ought to be able to fit at least the first 5 or so. First 5 modes of the drum. I did add a little bit to the ModelSim description using ModelSim. In particular, I added a little piece that showed how to export. It turns out you can export ModelSim as a spreadsheet, which nicely MATLAB can read. So you can export a waveform import it to MATLAB and just play it as using the sound command and listen to it. It should sound like a drum. If it sounds like skiwark, then probably you have an overflow problem. If it rips your eardrums out, you probably have an overflow problem. So you're going to want to do that. And in fact, we'll ask you to do that for this lab this week. So any questions? Anybody get a sound out over the weekend? That's asking a lot. Well, I thought I ought to show you the computation layout for that seems to be most effective for computing this. And that is to think of the square drum as consisting of columns that we can sweep through doing the calculation. So we're going to calculate all of these nodes in parallel, then these nodes, then these nodes, or vice versa, these, then these, then these. And the advantage of that is that we can scroll values out of memory into the computational units, write the results back into memory, and the communication between nodes this way gives us the nearest neighbors. So if we were to show one column of the calculation, it's going to look something like this. So we need a couple of memory blocks at the bottom. I'm going to represent these as M10K, but they need not be M10K. They might be MLab. And one of them is going to hold UN, and the other one is going to hold UN minus 1, because you remember there's two state variables for each node. And the output of these guys is going to be muxed with 0. We're going to call this mux A. Goes into some sort of compute module. And because we have to keep track of previous nodes for doing the calculation, we're going to need another register up here that you shift into. So you're going to shift a value out of here through the compute module and up to here so it can be used for the next calculation, the next node calculation, with another mux here that can shift in 0 for boundary conditions. The nearest neighbor communication will be either another node or or 0 if it's a boundary condition. If it's on the edge of the array, then you would shift in a 0 here. And the UN minus 1 would feed directly in here. And we have to be able to separately copy U to UN minus 1 after it is used. And we need to be able to write back the new value of UN from the compute module. So there's going to be a sequencer here that has to be running, which I'll talk about next. So what we're going to do is we're going to calculate all of row 1 then all of row 2, and then all of row 3. And this is sufficient in the sense that all we need to do to compute one module, all we need to compute one node is the value of its neighbors, east and west, the value of the neighbor above, the value of the neighbor below, and the last time step for the current value. So let me write out some steps here. Now, and this is going to be duplicated for as many columns as you're going to calculate. So what's limiting here? M10K blocks, we have, well, 400 of them. So that would be 200 rows, 200 columns. And 220 columns. Multipliers, we have 300. And so that would imply 300 columns. So it's actually moderately well balanced. So the sequence of operations now to compute one state is going to take 2 or 3 steps. So we're going to start out by saying we're going to copy row 1 from M10K to the compute module. And then 2, output row 2 from M10K. And at the same time, same operation, we're going to copy row 1 of compute. We're also going to copy, so this is Uij, we're going to copy UN minus 1 M10K to the compute module. And we can do that on the same cycle because it's 2 different memory blocks. Next we're going to compute the new row 1. Oh, but we can do one more thing here too. On this cycle, we can copy, we're not going to use, we've already used n minus 1. We've already moved n minus 1 to the compute. So we can copy un to un minus 1 for the row. Now we compute new row 1 because we have all the information. The current value of Uij is here. The current value of Uij minus 1 is here. The value of row 2 is here. We have to, oh yes, we also have to here, or before we do this compute, in any case, we need to, let me move this down, set the B mux to 0, and then 3, compute new row 1. And then the 4th step is we're going to shift old U let's call it old row 1 to this reg, write new row 1 back to the M10K block. So we're going to write this back to M10K and then start row 2. So there'll be about 4 steps. They may be able to be merged more. There'll be about 4 state steps where you shift the value out of here, shift this value simultaneously out of here, set this mux to 0 for the first row, compute, move this value back to here and the old value up to here, and then get ready for the next row, and then do the next row, and repeat. Except that at the last row, the very last row, when you get to the bottom, instead of shifting out a value that doesn't exist, you have to convert this to the A mux to 0 and shift to 0 in, you have to have a boundary condition of 0 by turning off this M10K block and turning on 0 here. So on the first row, this is going to be 0. On all the other rows, it's going to be the reg feeding back. On all rows except the bottom row, this is going to be set to the M10K block. And that uses the resource about as much as you can.
So the B mux is for the side boundaries, and the A mux is for the bottom boundary?
No, the B mux is for the top boundary.
Okay.
So this would be that you're going to turn the B mux to 0 when you're computing the top here. When you shift the first one in here, when you shift the top row in, there's no row above it.
Yeah.
Okay.
Okay, that makes sense. But yeah, you're just getting the boundaries from the sides.
The boundaries come from the sides, which are going to be either another compute row or 0. So in this case, you'd build one compute pipeline, which is fairly straightforward. This compute state might actually be more than one state. There might be several states necessary to add everything together, depending on how you pipeline it, or it might be done in one state if you slow the clock down a little bit. But then you take this whole pipeline and duplicate it, stamp it down as many times as you can until you run out of M10K blocks or multipliers, whichever comes first. Now, what happens if you run out of multipliers? If there's still logic left, Quartus will just start building multipliers out of logic. They're slower, but it'll still work. At least one group last year figured out that they could, how do they do this? No, I can't remember. They've managed to multiplex the whole compute structure somehow and do another set of rows. But I can't remember how that was done. Oh well. But this would get you something like 256 from the M10K block depth by 300. So it would be something like 60 or 70,000 nodes. Now, when I said 300,000 nodes was the record last year, I have to modify that slightly by saying last year I allowed symmetry. So if you computed this, you were allowed to count the whole drum. And this year I'm not allowing symmetry. You actually have to compute the nodes. It doesn't change anything except the number of the reported number of nodes. So 300,000 divided by 4 is 75,000. So it was this was about what they were doing last year. How do you do symmetry? Let's say you don't get any sort of numerical credit for it, but you can make a lower sound if you use symmetry because you've doubled the size of the drum. All right, speed of sound remains constant. That means the pitch goes down. So what are the boundary conditions if you're only going to compute 1/4 of the drum? But first of all, that means you have to only drive it exactly at the center with a symmetric drive. You can't hit it off center, you can't tap the edge of the drum. You have to hit it dead center with a symmetric excitation function. But let's say that you hit it dead center. You know the boundary condition along here is u equals 0, right? What's the boundary condition here? Yes?
I mean, just have your left, so for the vertical, have the right boundary condition be your left boundary condition. Or like, have your left, sorry, not left boundary. The node to your left is the boundary condition to the right.
You mean left and right across, reflected like that?
Yes.
Yes, because that guarantees 0 slope. And this has got to be, it's got to be a maximum or a minimum at the edge, right? And so reflecting this, if that's a boundary condition, reflecting this one over to here guarantees 0 slope across the boundary. I'm not asking you to do that. You get no extra credit this time for quoting more nodes because you use symmetry. I just want to see the number of nodes you compute at 48,000 times a second. You can fiddle around with moving the clock rate up. The M10K blocks will clock at 250 megahertz. The multipliers will clock at least 300 megahertz. We've been running state machines at 50. That makes it real easy to compute the timing. You don't even have to worry about the timing. Start turning the timing down. Start turning the clock rate up. Till it breaks. Catches on fire. I don't think it will actually destroy itself, although I'm not sure. If you look carefully at the board, there's a connector on there for a fan. Ooh, why would they put that on if you didn't need it? So I haven't felt these things run more than about 110 Fahrenheit. It starts to burn at about 120 to 130, and this was just below the level at which it was uncomfortable. So probably call it 110 Fahrenheit. That's easy, that's fine. If it burns you, it's too hot. Don't take the plastic shield off to touch the FPGA, however. You can touch it from the bottom. It's thermally connected to the circuit board. Ground yourself, ground your elbow. You put your hand against the bottom of the circuit board, see how hot it is. I don't think it'll be a problem. However, if you were to take the circuit board and nestle it down into ESD foam, like I've seen some people do, you might be able to cook it. So make sure that when it is sitting on an ESD mat with airflow underneath the board so that it can do a little bit of cooling. I made a plenum for mine. I took a cardboard box and cut a hole out that was the same size as the FPGA, and then cut a hole in the side of that cardboard box so you can go in like this and up against the FPGA. You can see it sitting on my desk. It's really cute. You can make one if you'd like also. I have some extra boxes. So what are you going to do here? It depends on how you like to think about it, right? You could. Is anybody tempted to try and get through this lab using only the HPS? I'm not sure it's easier. Ouch! The only problem with lecturing barefoot, well, in Phillips 101, it turns out there's plates like this in the floor that have plugs underneath, up in the front. And if people put those plugs in upside down, they have 2 wood screws sticking up, the points of 2 wood screws. I stood on one of those one day, jumped up on one and landed on it again. Yeah, all right. So you're going to find you need to copy. You have to make lots of copies of stuff. And so I did want to talk about generate statements just a little bit. There's a good Evans and Sutherland data sheet that's linked up. Where is it linked up? It is linked up. Verilog. Quick reference, Sutherland. Evans and Sutherland. HDL. I like that. I like it so much I decided I'd show you a page from it. It's on generate blocks. And the general form is that you can define variables, genvars, that exist only in the generate block at compile time. So they are compile time entities. They do not exist for synthesis. They only exist for bookkeeping during code elaboration. And these have to be 0 or positive integers. And oddly, the variable can be either defined just before, outside of a block, or inside the block. So you can put it outside the block or inside the block. I tend to put stuff inside the block that I'm generating. Inside of a generate block, you can generate anything you want. Variable declaration module instances, procedural blocks. You could have an if expression, generate a ton of stuff, else generate some other ton of stuff. You can have for next loops. For next loops. Oh dear, my background in BASIC is showing. For loops. And because the process is happening at compile time, these if, else, case, and for loop have to be constant expressions. They have to be evaluatable at compile time. They have to be evaluated at compile time. And because you're generating a group of hardware, it makes no sense to have variable lengths on the for loop, because how could the amount of hardware change that you're generating? That would mean that you're somehow dynamically changing the FPGA at runtime. That can't happen. So you can generate arrays of modules. You can generate arrays of connections between modules. And to make this slightly less abstract, I thought I ought to do an example, because after reading that, I know I couldn't figure out what it meant. So let's do a linear example where we're going to have a D flip-flop actually a shift register with some input shifted through to an output and we're going to call this signal path 0. This signal will be path 8, 8-bit shift register. We're going to assume that we have a module called D-flop. D-flop, which has a clock, an in and an out. And what we want to do is generate this array of flip-flops. So we're going to have some module, top-level module, which has a clock and an output. No begin there. Has an input, clock, a register of 3 down to 0. Yeah, okay. Of count. So a short counter. A wire of 8 down to 0 of path, which we're going to index into. And an output of out. And we're just going to say, to generate a clock, always at edge of clock count gets count plus 1. And we're going to assign path 0 to be sort of arbitrarily count 3. So what that means is that this will go high every 16 counts, stay count high for a while, and then go low again. And we're going to assign out to be path 8. So we're going to have our genvar n, which is going to be some counter that we use, and then we generate. For n equals 0, looks weirdly C-like, n less than or equal to 7, n equals n plus 1, begin, but now you have to give it a name. And so we're going to call this flops, flip-flops, right? And we're going to say that we want a D flop, which we know has clock in and out. And we have to give this a name. We'll just call it U. And I believe what happens is that the generate module prepends flops to U and then postpends an index to make unique module names. Dot clock gets an input of clock. Dot in gets a path n, and dot out gets a connection of path n plus 1. N plus 1. So we end the for loop, we end the generate. I forgot, there's more board. End generate, end module. So we can use a counting index to generate an array of wires connecting together an array of modules, which is precisely what you would do is if you were building a set of columns of compute elements side by side, or which you can do in 2 dimensions with a nested loop for building a 2D array of compute modules. You don't have to do this. You can name the wires by hand and hook them together. Very error prone. But you're probably going to want to use some sort of generate structure, either to generate a one-dimensional set of compute columns or a 2-dimensional set of multiple node computers.
So if we're at the boundary, can we just do something like if we're at the bound in the for loop, can we just do like if at the boundary, tie this to ground?
Yes.
Okay.
Yeah. So what are people leaning towards? Blocks, columns, or something else? Blocks, columns. Blocks, columns. You're columns. You're a column guy. Column. Blocks, anybody? How about other structures? How about checkerboard odd even? Let's say you wanted to only use the HPS. You could break the system down into left side and right side with a boundary across the two, which is shared memory. Ew. I don't recommend this, by the way. The HPS is fast, but it's not as fast as all that parallel hardware.
Have you played around at all with using the HPS without Linux, like doing bare metal?
Oh, the pain. So the first week I was using this board, I tried to run the HPS bare metal because I'm used to programming in C with memory maps and stuff. But it turns out that, and I could get it running, and the ARM comes up at 50 megahertz, which is the provided clock input to it. And I'd really like it to go 850 or 900 megahertz, which is the rated speed. After 2 days of reading, I decided I couldn't figure out how to set up the phase lock loop. The number of dependencies in setting up the phase lock loop is great enough that it wasn't cost effective. An ARM9 bare metal is really complicated. Tell you how complicated it was. It took Tom over 24 programming hours to turn on a timer. Turn it on, not get the interrupts running. Just make it tick. Oh, well, it turns out there was 2 levels of indirection in enabling of the clock, of the feed to the clock, the time base to the clock. Just unbelievably hard. That's when I decided I was not going to do it bare metal. However, if you want to, figure out how to get it running, the C compiler works perfectly fine bare metal. Actually, not the onboard C compiler. The C compiler that runs in the Altera monitor, it's a cross compiler. You have to, it's still GCC, but you have to run it on the PC and then download the design through the USB connection to the HPS. So any questions at this point about the lab? You might, so one approach is, one person starts figuring out how to take my sine wave example, which makes a tone, export it to MATLAB and listen to it. Get that whole export chain running without doing any. Another person does the simulation of one node to get a sine wave out and maybe takes it up to 4 nodes and listens to it using sine wave. While another person starts worrying about the bus master, the audio bus master. I will go through the audio bus master stuff again Wednesday, because I think it's been too long since I did that. Questions?
If we just want to use an if statement, we use generate or always?
Those are completely different. Generate, an if and a generate generates is a conditional compile, right? It either generates hardware or it doesn't. An if statement in an always block is asking at runtime if a condition is true or not. It's a completely different level of abstraction. So these if statements only have data, only run at compile time, never in production. There is no such, the stuff that's, all of these statements disappear after the hardware has been generated. So they're not interchangeable in any way. See see you tomorrow or Wednesday or sometime.